All right, so we're beginning chapter 11, starting obviously at 11.1. Now, what we're going to do, and what I highly suggest you do, is have a piece of paper set aside, a separate piece of paper to be taking down tables. You can memorize this entire chapter, and it'll be great. It'll be useful. It'll help you out, but there's no need to. This chapter gives a preface of an understanding of the use of trigonometry. However, there's no need to memorize all these whenever you can have reference material. And then basically, you can reference different parts of your material depending on the problem that you've been presented. That will make sense as we move along throughout this chapter. Okay, so as we come along, I'll point out certain areas. Let's make sure that you're actually writing down those tables and have them set off to the side. Especially for testing purposes, you're going to want to use it. It will help tremendously. And then it'll be like, oh, I can go use this. Then all you do is, I found this, let's plug it in right here because this is where it belongs. Yay, and that's easy. That makes math easy. Okay, so 11.1 is discussing the law of sines. The law of sines. Basically what we are presented with is a triangle that does not have a right angle in it. Okay, if you look at the example given at the top of the page, we have basically this triangle. However, within this triangle, we can actually have a right triangle present, again, within it. Now, whenever we determine the area of a triangle, that is 1/2 base times the height. Okay, that kind of takes us back into some geometry in this. But we've also learned it earlier on in school. So if you have the height here, and we'll be consistent, capital A meaning this angle A, capital B, capital C, and again to recap, the capital letters represent those angles for that part of the triangle. The opposite sides are lowercase, and they represent the length of the sides opposite that angle. So the opposite of angle C is going to be lowercase c. Opposite of A is going to be lowercase a, and B is lowercase b. Now here we have a right triangle developed, and this will be uppercase D. But again, this just represents that is a right triangle. So within the area, we can have 1/2 A times H. A meaning the length of this entire larger triangle. 1/2 the base times the height. Now we're going to use this area and trigonometry. We're going to kind of take this hand in hand, a little bit of geometry, a little bit of trigonometry, to be able to solve some of these unknowns. What first we have to understand is ways that we can use sine to help us out. Now again, what is sine? Sine is opposite over hypotenuse. Okay, opposite over hypotenuse. So if we look at angle ADC, within this triangle here, what is going to be the sine of C? What is the opposite side and what is the hypotenuse?
The hypotenuse is B.
Okay, the hypotenuse is B. And what is the opposite side? H, absolutely. Okay, so the sine of C is going to be H over B. We all follow along so far? Okay. Now, whenever we have the area of 1/2 A over H, then what we can do is we can substitute H and apply this portion over to this portion. So let me ask you this. For area, for the triangle ABC, we can do 1/2, I'm just going to give this to you, AB sine of C. Okay, I'm jumping ahead of what the book is telling us we can use so that we can go backtrack and understand why. Okay, I think this will be a little bit more simple. So if we know that the sine of C equals H over B, how can we get to the area of triangle ABC equals 1/2 A times B times the sine of C? How can we get there? If we also know that triangle ABC is 1/2 A times H, how do we get to ABC equaling 1/2 A times B times the sine of C? So let's look at this. We know that the sine of C is the height, which is the opposite side, times the hypotenuse. Okay, so from here, I'm going to erase this bottom part here since we rewrote it up here. Let's solve for H and discover what its value is. Well, by doing that, we take the inverse operation and multiply both sides times B. So then H will equal B times the sine of C. Okay? Well, here we've used H to find the area. Well, now we can substitute this information here for H. Okay, we can take out H, completely remove it, and plug in this information here. Does that make sense?
Yeah.
Well, and that's how we're getting here. So we have this 1/2 A, and then we're plugging in this information here, B times the sine of C. And really, since we're multiplying, we can get rid of the parentheses, and we simply have this right here. And this needs to be a capital C, because we're talking about the angle measure of C. So we have two different ways that we can find the area. This is great if we have the base and we know the height. But what if we have the height and we have the measure of this side over here and then this angle measure? We can still find the area, and we would have to use this form in order to be able to do it. Make sense? Okay, let's see if this really does make sense to you. All right, you're getting great. Darn it, I knew he was going to do that to us. All right. So I want everybody with your piece of paper. I'm going to leave this part up here. But what if we were given this angle measure here? We used C, this angle measure C, to be able to determine the area of this overall triangle. given the same information, what if we were given the angle measure of B? How would this change? You'll take a few minutes, try to work through it, and see what we come up with. This is going to be fun because I'm waiting to see the light bulbs start to go off, and they will. It'll work. You're like, oh yeah, I can do that. And then once you do that, it's going to open up even so much more. Well, if I can do that, well now I can do this over here, and we're about to see that happen. Now what's interesting, and I hope you are finding out, that somewhere in here, whenever you're utilizing this information, our goal is to substitute H. So H has to be involved. Keep H involved in what we're doing so that we can transfer that over. Or A, that's another interesting point. One of these we're going to be substituting. But how? We most likely won't substitute the half. It's a hint. And I like to make some confusion right now with this.
Wait, what was the main question again?
We're using, earlier how we went to this format was because we had this angle measure, C. Well, so we saw how we can take what we used to know or one way of determining area, but if we don't have all of our information, the base and the height, how can we use this angle measure to help us still find the area? And that's how we ended up with this. Well, now we're switching it. We found how we can use the angle measure of C to end up with this. How would we use it with having the angle measure of B? So you will have B involved in here somehow.
Would it be triangle ABC equals 1/2 A sin BC?
So it'd be 1/2 A what?
A sin.
Sine? Okay.
Fine, yeah. Whatever. BC?
BC?
Yeah. No,
is
CB. Yeah, no, BC.
So it's this. Now what's important is we have to take the sine of the angle. Okay, C. So which one do you have capitalized and which one is?
Oh, capitalized B.
Okay.
And then a lowercase c.
Okay, so it'd be A times C times the sine of B. And that's really what this is saying here. The area of triangle ABC equals 1/2 A times B times the sine of C. So same thing here. What you're saying is 1/2 times A times C times the sine of B. And that's what you have? Okay?
That's what I got too.
All right? Really?
Yeah.
Cool. Wait, you don't believe me? Here it is.
I had
All right.
to get it done a second time.
So let's see what we have here. Since we're looking at, and you are using sine of B, so sine again meaning opposite over hypotenuse. So the sine of B, angle B, equals H over C. You'll have that so far?
Mm-hmm.
Okay. So then again, to get h by itself, we're going to multiply both sides. So we have c times the sine of b equals h. Well, we can take h out of this and plug in that information right there, which gives us 1/2 times a times c times this sine of b. And there you have it.
'Cause
Very
you're
good.
You're replacing the b, well, like in the original equation, like it's the
Sine. It's okay.
c, and so you're trying to find the b this time, so you just switch it out with it.
Right.
And then you switch the b with the whatever. Well, the hypotenuse on the c side is b, and the one on the b side is c, so you just switch them.
Correct. Correct. So now, what if what about cosine?
Isn't that
Let me ask you this. Okay, so let's talk. Yes, what is cosine first of all?
adjacent over hypotenuse?
Yep. Cosine is adjacent over hypotenuse. Okay, so let's still look at, we'll do this. A, B, C equals 1/2 A, B sine of, A, B, C sine of B. All right, let me back up real quick before we go into cosine. What about angle A? We've used C and we used B. What do you think about angle A?
Well, which side are we doing?
It would be A over C. Should we write it out?
That's a really good question.
Because it's part of both of them.
Angle A is actually this right here, that entire angle, and again, this side A is the entire length of this side. So what do you think about using A in this capacity?
Would you do half of it?
Is that half of it?
No.
No,
How do you know?
because one angle is smaller than the other.
Visually, it's smaller.
Well, it would have to be, right?
Would it?
Yeah.
Why?
Because one line of this would have to be the C curve.
So this would actually have to bisect that angle. And we have to be able to prove that the height actually bisects that angle into two equal angles. We don't have that information. You would think, common sense would cause you to believe that it wouldn't, but in math we have to have proof. We actually have to show that it either is or isn't. So since we have this, we're not going to use A necessarily. Go ahead.
Would we do just like take out the line in the middle and we'd do that entire triangle, like, well, it's not a perfect triangle, but when we do it, so it'd be like,
But we have to know the height.
not necessarily, right? I mean, it's adjacent, which would be A, or no, yeah, A, lowercase a, over hypotenuse, which would be the larger c, or the small c.
Okay, so what is the height of the triangle?
I don't know, that's not true.
And that's where it's stickiness. Because we're using, in order to find the area, it is 1/2 the base times the height. So we have to, in some way, understand what the base is and understand the height. And we have to be able to utilize that. So in this situation, we're not going to use A, but we can use C or B to help us out. We can use both to confirm our answers. What's interesting is if you were given values for both of these and you had an answer, let's say it was 50.5. Whenever you plugged in all of your information, both of these will result in an answer of, I wrote these down wrong, and I did that. This should be C, this should be B. Will result in 50.5, okay? Because all we're doing is substituting the same information, even though we're going about it a different way, we will still result in the same answer. So if this equals 50.5, this answer will result in 50.5, and so will this. But again, we're not going to be using angle A. We'll only be using C or B. So let me ask you this. What about, let's go back to the original question, what about cosine? Can we use cosine in the midst of this? We've used sine and we found how we can use sine. Would you be able to use adjacent over hypotenuse to be able to do some substituting?
Yeah, good.
No, I don't think so.
So let's see, cosine of B equals adjacent over hypotenuse. Okay, why can't, just with what we're given here, only this information, why can we not use cosine?
Because it's the A is part of both of them, and so it extends more. It's not just that side; it's also that
And-
side.
Yes, it encompasses both of these sides here. Okay, keep that in the back of your mind, okay? So, and we can't do that because let's say we got rid of this here. Where's our hypotenuse?
A. Right.
When does a hypotenuse exist?
When they're for 90 degrees.
When we have a right triangle. This is no longer a right triangle when we remove that. So we no longer have the hypotenuse, which kind of eliminates our ability to use this format. Okay? So now, what's interesting about that is, let's say if we have and we're going into section point 2. We'll stop right here because the next section will address this very problem right here. Okay? So does everybody feel pretty confident so far with this information that we've gone over? Okay, if you remember sine is opposite over hypotenuse, then you're able to accomplish this. Okay? Now, if you look at example number 2
On 11 point.
on 11.1.
Oh.
11.1. Here we are given, I'm going to keep all of this information up for right now, but here we are given this. We have a triangle that's going to be angles x, y, z. So we have capital X, capital Y, capital Z. And then we have sides x, y, and z. We are given that the angle of x is 61, the length of side x is 5, and the length of side z is 8. Now, what we are able to do is, if we have these 3 pieces of information, then we are able to find out what the missing 3 pieces are. Okay? By using the same format that we used here. Okay? So if we have this triangle, 8, 5, 61. Okay? We can do the same thing here. Understanding the same ratio. In fact, once we do this, we really don't have to draw it except to help us visually, but we can make what we do know and combine with our unknown. So here we can take, and this board is getting full. Does everybody have this written down here?
No. Oh, well, yeah, actually. I do.
Oh, yeah.
Will you? Okay, good. Because this is getting confusing with all this stuff up here. So, we can take the sine of x over the sine of x, and that will equal the sine of z over side z.
Mhm.
All right. Now, just like in transferring from, basically we can plug in our three pieces and find out what the fourth unknown is. Okay, because they're all relative to each other, we can take the sine of 61 degrees divided by 5 equals the sine of z over 8. Plug this stuff into your calculator and come up with an actual value for it. You'll divide it by 5, then multiply it times 8, and that will give you your answer. So you have 8 times the sine of 61 over, well, back up. Divided by 5 equals the sine of z. Okay, you will have a value. Now, don't make the mistake of multiplying this top first and then dividing by 5, you will get a different answer. Because right now it is the sine of 61 degrees divided by 5, and then you're going to multiply that times 8. Okay?
Mhm.
And then you will, that numerical result will be the answer. The sine of z will be that. Okay? Now, what does that mean? The sine of z gives you an answer. You have to find the degree of it, the actual degree measure. Because notice, it's not 61 degrees, it's the sine of 61 degrees. So in the book, we find out that the sine of z, after we go through all the calculations, is going to be about 1 point, it says 1.399. And then we can actually figure out what our degree measure is. Now, what's interesting about this, okay, is okay, let's hold on to that. Take this away. Oh, I want to keep that. Let's keep that. Now, we're going to go back to example 1 in 11.1. We're going to go back to example number 1, 11.1. Here, we are given, again, 3 bits of information. A, B, C. A, B, C. Here, we are given 2 angle measures, 38 degrees, 65 degrees, and then we have this length of 16.
But since we know the 2 degrees, we already know it.
Perfect. Yes. Since we know 2 degrees,
Oh, yeah.
now we can find the third one. So how do we find that?
But we just add them together and then subtract by 180.
Yes, absolutely. So we have 180 minus, was it 38 plus 65? And we will end up with this one here, which is
85. Right?
77. Because those two added together, let's see,
Oh,
90,
38, I thought it
103.
was 30.
Yeah, 77. So we know this one's 77 degrees. Perfect. So now we can use our ratios to find out missing pieces. All right, so we can do sine of 38, sine of 38 degrees over 16 equals sine of 65 degrees over b. So what we need to do is calculate what is the sine of 38 degrees, what is the sine of 65 degrees. We have, and basically what's going to happen, whenever b is on the bottom, we need to find out what b is, okay? So what we are doing is we're basically going to cross multiply. We have b times the sine of 38 degrees equals 16 sine of 65 degrees. Well, we need b by itself, so we got to divide both by, I keep trying to, sine of 38 degrees, sine of 38 degrees. Okay? And that will cancel out, and we will have b by itself. So b equals 16 times the sine of 65 degrees divided by the sine of 38 degrees. Then we will actually have the value of sine b. Then we can do the same thing to find c. Okay?
Yeah.
All right. That is helpful. That will help us get there. We have one problem, a big problem, whenever we use example 2. When we go to example 2, if you read here in this section, we need to recognize that a value greater than 1 for sine z is impossible. But if you don't recognize that, your calculator will. It'll show error on there. Okay? It will show error. So, what that means is, let's move over to section 11.2, and let's read the top of this. Because now, what we've been discussing so far is the law of sine. We basically just using sine to help us determine information about these triangles. However, there are certain when we cannot use it because we're going to find errors. We have to go through it a different way. So it says, if you know two sides and an included angle, or three sides of the triangle, you will not be able to solve the triangle by using the law of sines. So earlier, we had two sides and one angle. That is one of those instances when we cannot use the law of sine. Whenever you have sine of an angle and it's going to be greater than 1, it will be an error. Okay, so it's something kind of good to know. Or if all you have are all the three sides but none of the angles, you will not be able to use the law of sine. So does that mean we give up and we're like, oh, so can't use it, it's impossible?
Yeah.
No, because he has his little cousin over there saying, oh, well, I know what to do. And that's where we go into law of cosines.
Oh.
Yeah, I know. Isn't that awesome?
I always hate that.
Law of cosines. So, first of all, before I remove this, do we have any questions? So, if you have at least two angles, and one of the sides, then you will be able to figure this out.
On that
Okay.
triangle, since we know all three of the angles, if you just drew a straight line down from B and made it a right angle,
Mhm.
can't you use that to find the length of
How do you
side?
measure it? You have to know at least one of the sides to know how to figure out the other sides. If all you have are 3 angles,
We have the line BC equals 60, whatever.
the line, yes, if you have the length of that, either one of the sides, or like we found, if you know the height, then that gives us some information to use.
Instead of going through all that, like on this example,
Well, on,
maybe.
I guess I'm trying to understand what your question is. On 11.1, which example are you talking about?
Example 1.
Example 1. And so you're saying,
From if you drew a straight line down from BC and made a right angle, then you would know the 3 angles still.
well, you know the 3 angles of the triangle, the larger triangle. 65, you don't know how it's split up.
Oh,
Now, you can figure it out. So the question was this, before we go there, does everybody have this information down? So I can erase this stuff. Okay. Because this is a good question. And what this is talking about this is going to help us. When do we create a right triangle? And when is creating a right triangle actually causing more work for us? So this is a really good question. So in example 1, we have this. We are given 65 degrees, 38 degrees, and with a side of 16. And so we have A, B, and C. So we can make a right triangle here. Visually doesn't have to be accurate, but we can actually have a line going from this angle perpendicular to here that creates a right angle, and then just identify that it's a right angle. We won't know this length, this side here. We do know that this is 77 degrees.
then we could figure out the small angle.
Absolutely, we can, because we have 77, we have 90, and then we can figure out what that angle is.
And then can we figure out the other 2 sides of that smaller triangle? And then
However, by doing this is creating more work for us. Now that we know the law of sines, we don't need that. We don't have to, now that we know actually all 3 of the angles and one of the sides, we can use the law of sines to cut down our workload. You no longer have to make 2 triangles. You can just understand that the sine of A over 16 equals the sine of 77 over C, side C. Okay, which means, so we have the sine of 38 degrees, and so this we can calculate, this we can calculate, this we already have, and so now we just do some multiplication and division to figure out what side C is without having to draw anymore. Okay. But the fact that you're even thinking of that as an option is really good, because there may be circumstances that we're about to find out. Actually, it's a great lead-in question. There are circumstances when we cannot use the law of sines, so we have to do this.
right.
Okay? Since you were so smart in asking that question, let's try an example out and see where it goes. You're like,
Great,
so
Bill. Thank you.
never again will I ask a question.
More.
Actually, it really is, for you, it's good that you asked that question, because it's going to help your understanding of this next section. So, 11.2. Just like we were talking about, if you know 2 sides and 1 angle, or 3 sides and no angles, we will not be able to use the law of sines.
Yep.
However, we can use the law of cosines. So let's use this example here. we have? We have side C. Let's see, angles A, B, C. That's A. And then here we have our right triangle that has been developed. Our height. This will be D. Now, and I almost don't like the way that they put this. It'll make sense. We'll stick with what they have. So notice B, in the past whenever we were looking at this, we have side B. Okay, and that encompasses this whole side here. However, we're going to, for this example, we're going to rename this. This side is going to be X, and then this side right here is going to be B minus X. Okay, and we understand why this exists. So this is what we're going to be working with. Realistically, what this should be is we have all of side B, and this should be B. I'll just forget that. Let's stick with this because I'm just going to confuse you if I try to explain it otherwise. We'll stick with what the book has. That way, if you have any other questions, you can go back and see the example that the book has written down. So we'll stick with this. So this side right here is X. This side is B minus X. Okay? Because you have the whole length of B, and then whenever you take away X, this here will be B minus X. Everybody on board with that? Awesome. So here we're going to use the Pythagorean theorem to assist us with this. The Pythagorean theorem being a squared plus b squared equals c squared. Okay? Within this situation here, we have the, we can actually change that over by using h, okay, our height within this smaller triangle or this smaller triangle. Now, whenever we're dealing with triangle A, B, D, notice D here, then we're going to have, and in the Pythagorean theorem, what is C always? Hmm?
What is C?
Yes, on the triangle, what side is C always?
Oh,
The hypotenuse. Okay, so you have whatever leg plus squared plus whatever leg squared equals the hypotenuse squared. All right, so in this situation, we will have c squared equals x squared plus h squared. This leg squared plus this leg squared equals that leg squared. Does it matter if it's h squared plus x squared? Does this matter which one we use? No, it doesn't matter at all. So don't worry about that order. Okay, but you can do that. So now, likewise, and that's for this triangle here, likewise with this triangle and triangle B, CD, we can call it, it will be a squared equals h squared plus b minus x squared. Because b minus x is this side right here, and we have to square that whole side. Does that make sense? All right. So b minus x squared, let's come over here. B minus x squared is the same thing as b minus x times b minus x. That gives us b squared, because we use the FOIL method to figure this out, b squared minus xb plus x squared, or b squared minus 2xb plus x squared. Now, if, again, this doesn't matter if it's xb or bx because those are multiplied, so however it shows it that way. So, what that means is we will have a squared equals b squared minus 2bx plus x squared plus h squared. Okay? Do we see how we got from here to here? Okay, good. Now, what we can do with this is we can take this information and actually substitute. Okay, we can substitute. What we see here, in this, because again we're relating triangles, we have this, and we have that right there. Those are both the same. So what that allows us to do is a squared equals b2 minus 2bx plus c squared. Since c squared equals this, x squared plus h squared, we have an x squared plus h squared here. We can take that out and substitute c squared in place of it. Okay? Does that make sense how we got there?
Mm-hmm.
All right. This is basically proof that is going to allow us to do what we're about to do. Okay? This is showing why we are able to do this, which is very important. Okay, so we set up to use h when in all actuality we're really not going to use, or don't have to use h. There may be times whenever we do if we're given what that is. So here, now we're simply using the sides that we were originally given. Okay? Now, finally, what we can determine is, for instance, the cosine of, and this is gonna be interesting. We'll walk through it. In triangle ABD, okay, we have the cosine of A being what? What is the cosine of angle A? Because do you remember what cosine is? What? Cosine in general is what? Adjacent over hypotenuse. So what is the adjacent angle to A?
X.
X. And what is the hypotenuse in this triangle here?
C.
C. So cosine of A is going to be x over c. And likewise, which if we bring this down, x is going to be side C times the cosine of angle A. So what that allows us to do is we can substitute out x and put in c cosine of A, c times the cosine of A, in place of where we have an x down here. So this will give us a squared equals b squared minus 2 times b times c times the cosine of angle A plus c squared. Okay? Now, so we walked through the proof. Does everybody see how we started with this? We worked our way through using the Pythagorean theorem to get to this point. Okay. The beauty behind what we did now is really, it's great to know so that you know that you can use substitution for information and work your way through. Now, if you look over there in your book, on the right above example 1, you will see law of cosines. Write that down so that you don't have to go through this every single time. All right? This is the beauty behind it. Because we are able to do this, we have some consistency. Where we have a squared, and another way of writing this is a squared equals b squared plus c squared minus 2bc cosine of a. Likewise, if we want to use b, we can do b squared equals a squared plus c squared minus 2ac cosine of b. Notice how this is being moved around. C squared equals a squared plus b squared minus 2ab cosine of c. If you forget your piece of paper, you can recognize that these first two are the other two sides, minus 2 times the other two sides times the cosine of this side here. So y'all kind of see the pattern. With b equals the other two sides added together and they're squared, minus 2 times both of those two sides cosine of this one here. All right, so have that down, have access to it, because if you were given 3 sides or 1 angle and 2 sides, then you're going to need to use the law of cosine to figure this out. So can I erase all this? Are we all good? All right, we're going to try one and then we will move on. Super. Been waiting for this one. Going to keep this up there. All right, so we have this triangle here. We have x, y, z, and we have 8, 12, and 10. So, what I suggest you do, first of all, since we're using this, how about we change these? You can redraw it and make it A, B, and C. Because since we're using this, A's, B's, and C's, well then let's keep that consistent, so just rewrite it. So, now that we know this is A, we can find that, again, identifying that the opposite side of that angle, so lowercase a will be opposite of angle A, this will be C, and this will be B. If you can visually recognize that, great. If not, identify it. Mark it on your drawing so that you don't make mistakes. Okay? So let's figure out angle A. So since we're going to be we're going to use the law of cosines for angle A, we're going to use this first one up here. So we know that we will have a squared equals b squared plus c squared minus 2bc cosine of angle A. So we will have 10 squared equals 12 squared plus 8 squared minus 2 times 12 times 8 times the cosine of angle A.
Okay.
So we can square all the numbers here.
Yeah, absolutely. And now we're not going to go through all of this, but just for time's sake, but this is all calculator work here.
Yeah,
So-
you could probably do most of it in your head.
What's that?
You could probably do it in your head.
Well, you can simplify this, so you have 100 equals 144 plus 64 minus, what was that, 896, so 180, 192 minus 192 times the cosine of A. And so you add these together, and you're going to subtract, then you're going to divide. So here you have 100 minus 208 equals a negative 192 cosine of A. So this is minus 108 divided by minus 192 equals cosine of A. And then the rest you do in your calculator.
Right.
Make sense?
Mhm.
So now it's a little bit of work and a little bit of writing, but it's not hard work. Okay, so and that found angle A. Now you got to do the same thing for each of the other two angles. Yeah, I know. So like I said, it's a little bit of work, but it's not hard work. Okay? Just make sure you are paying attention to using the correct one. Okay, depending on what angle you're looking for. Sound good?
Yeah.
I bet you are just excited that you didn't have to go through all that other mess again just to get to this point. But now you know how to. Any questions?
No.
No? Can I erase this? Awesome. Now likewise, if you had one angle and two of the sides, you can still go through this same process. You can still use this and just type in, let's say you knew angle A, you can just plug in the cosine, whatever the degree is, cosine, and you have a numerical value for that part right there. And let's say you were missing B or something, but you had side A and side C. Well, then you just solve for B. Okay? Yes.
On the homework, it says classify, on the first one, it says classify the information for each triangle, SS, S, SSA.
Side, side, side.
Yes, I don't want you to do that. In fact, I think I have that in the homework assignment. Did I say that on the homework assignment?
No, you just, on 11.5 you said no need to name the reason.
Yeah, on this homework, 11.2, yes, I don't want you to identify it. I want you to, actually, you know what? I do want you to do that.
Classify?
Yes, just, you don't have to worry about side, or angle, side, angle. Just identify if it's law of sine or law of cosine,
Oh, okay.
okay? I forgot what my
So
intention
not
was
the
there.
classify though.
Yes, I'm not worried about the angle, side, angle, side. Basically, all that's saying is what information do you have? If you have one angle and two sides, well then it's side, side, or angle, side, depending on what order it's in. I'm not worried about that. Just identify which law you would use. Alrighty. Now, problem solving. This is actually going to be interesting. This will actually, understanding this information here, is going to make your life easier when it comes time to taking, like, let's say your PSAT or SAT, and you have some of these distant travel problems. We found other ways to identify and calculate travel, but now we can use trigonometry to help us with this. So let's go over example 1. We are told 2 jets take off from the same airport at the same time. One travels an average speed of 510 knots which is nautical miles per hour, while the other travels 420 knots, also nautical miles per hour. The angle between their paths is 56 degrees. How far apart are the two jets after a half hour? All right, so we have this point here that they start off with. One jet goes this way, one jet goes this way. All right, they leave at an angle of 56 degrees from each other. Now, we're trying to find out what is their distance after 30 minutes.
Pretty far.
Well, what's that?
Pretty far.
Kinda. There's a length to it,
Yeah.
which is helpful.
Yeah.
So we know that the first one was traveling 510 knots, or 500 nautical miles per hour. How far would he have traveled in 30 minutes?
Half.
Half that. Okay, so what is half of 510?
355.
Close. 255?
255? Is it? Oh yeah, 255.
Okay, so at this point, this is the 30-minute mark here, okay? We'll get rid of that. This is where he goes in 30 minutes, and this is how far this one will go in 30 minutes, and we're trying to find that distance there. So the other one went 420, so in 30 minutes, how far would he have gone?
Yeah,
Good.
210.
210. 210.
Wait, I have a question.
Okay.
How do we figure that out? 'Cause I know there's a really simple way to do it. I just don't remember how to do it.
Well,
Like when you transfer the 30 minutes and like figure out how far they've gone.
oh, well, if we know that knots are nautical miles per hour,
Just like
we're staying in nautical miles, and it's just, that's how fast they're going per hour. Well, in 30 minutes, it's simply half that distance. After 1 hour, they would have traveled 510. Well, in 30 minutes, it'd just simply be half that distance.
Okay, got
And
it.
so that's how we're getting that.
Knew there was a simple.
Yes, and there is. So, we have one angle and two sides. We want to find out that right there, that side right there. Which law are we going to use? Sine or cosine?
Because
Very good. Cosine, why?
we have two sides and
Yes, we have two sides and one angle. And that's what's throwing us. Is if we have one angle or less, we're not going to be able to use the law of sine. Okay, we have to have two angles or all three angles. But if you have two angles, you can figure out the third angle in order to use the law of sine. So since we don't, we know we're going to use the law of cosine. So, y'all tell me which one am I going to use?
the top one.
The top one. Very good. So, because we're trying to find that, we will have a squared equals, now again, let's make sure until you're absolutely used to it, let's go ahead and mark all of our sides appropriately, with lowercase c being across from angle c, so that we don't get confused because it's a lot of writing. So let's make sure we have that. So we will have 210 squared plus 255 squared minus 2 times 210 times 255 times the cosine of 56 of 56 degrees. So what's going to happen is we're going to calculate all of this stuff. We'll have a squared equals some number here, and the cosine of 56 degrees, you can use our calculator or the back of your book and find a numerical value for that. Once you get all these numbers here, we have a squared, so we were going to have to take the square root of it. All right? So we can go ahead and do this. I'm going to have to use my calculator because I can't do 210 squared. So we have 44,100 plus 65,025 minus 210 times 255 equals times minus 107,100. That is going to be times, degrees, times 0.559 times so a squared equals, that is going to be 109,125 minus 59,889.6, let's say. And then subtract that, and then now we're going to take, we have to take the square root of both sides to get a by itself. And we find that it is going to be 222 miles for here. Okay? Does that make sense?
Yeah.
That wasn't hard, was it?
No.
So first I know it was pretty easy, and at first okay, law of sine, oh my goodness, I can't get this. And then law, great, now we've got another law. So already we're recognizing, well, we got to use the law of cosine. Oh, that's easy. I knew that all day.
No.
So, well, now part of the day.
30 minutes ago.
Exactly. And now it's just a matter of going back to our formulas, which we know how we got there. Okay, but now that we know, we can actually write them down and just refer to the correct one, plug in the information we know, and find the unknown. And it's that easy.
It's so easy.
It's that easy. Now, some of it will be finding side, some of it will be finding angle measure. It just depends on what it is that you're missing, but you can put that in. But the lesson learned behind that is identify which law you're going to use. Draw your diagram and put in all your information, and visually you can determine what law you're going to use and what you're going to need. What is it that I don't have? All right, let's move on to 11.4 to go over some basic identities. And this is going to be important as well. This is going to be another section where we need to write down information, but we'll discuss it first, but then basically just record it and use it as a resource so that you know which one you need to use. Sometimes you will need to use more than one because of the substitution process that we just learned. So first of all, let's look at this. It says an equation that is true for all values in the domain of the variable in an identity. An identity is an unchanging truth no matter what value the variable represents. For example, are y'all lost so far?
Yes.
Yeah, I know. You know, words just mess things up, but whatever. So, but this is the important piece right here. Cotangent of theta. Theta basically meaning an angle measure that we're going to be identifying. That equals 1 over the tangent of theta. Okay? Where theta is not equal to 0, okay, by definition. But whenever we're looking at cotangent, that equals 1 over tangent. So you can find the tangent. In order to find cotangent, then you can take 1, divide it by, on your calculator, tangent times whatever that angle is. We'll take that value, divide it in, take 1 divided by that value, and you will discover what the cotangent is. Okay? Likewise, the cosecant of theta is 1 over sine, and then the secant of theta is 1 over cosine. Okay? All right. So these are called the reciprocal identity. I'm not interested in you memorizing that these are the reciprocal identity, but understand that it is the reciprocal. Cotangent is the reciprocal ratio of 1 over the tangent. Cosecant is 1 over sine, secant is 1 over cosine. Have that written down. Eventually you're going to use it, and you're not even going to have to use your little chart anymore. You'll just remember that. Okay? 2 more. This is called the quotient identity. Again, mainly just write these down so you have them. The tangent of theta equals the sine of theta over the cosine of theta. The cotangent of theta is going to be cosine theta over the sine of theta. Okay, everybody have that written down? Okay. I want to walk through this proof with you, just to show you, because it's not that we need to prove it, but I think it will open up some of the possibilities of being able to use substitution to help you out, and that's the reason I want to go through this. It's always good to have your proof, but we're saying that it is. So let's look at this. We start off by saying sine theta over the cosine of theta equals itself. Okay, pretty simple, right? 1 equals 1. If we go back into, this is discussed in geometry, but then also even in our earlier algebras, 1 equals 1. So sine over theta, sine of theta over cosine of theta equals itself. All right, so what we were to do then, if we have, and y'all look at page 459, if you see the triangle up top, we're actually going to take these signs and we'll use this. B, C, A, C, A, B. We'll use this as an example. So again, understanding what sine and cosine is. So the sine of theta, and we'll talk about this angle measure here. The sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Well, do we like to divide fractions by fractions? No, we don't. We like to rename it. So it will be BC times the reciprocal of this bottom fraction, C over A. Well, since we're multiplying, we can actually cancel these two C's out. Okay, C divided by C is just 1. So we can eliminate that, which gives us B over A. Well, what is tangent? If sine is opposite over hypotenuse, what's tangent?
Hypotenuse over.
Tangent doesn't use hypotenuse.
Oh yeah.
So it's
Adjacent over.
tangent equals the opposite over adjacent. Okay? Tangent is opposite over adjacent. Well, in talking about theta here, this angle, opposite over adjacent, B over A, so we've proven that sine of theta over cosine of theta does actually equal tangent of theta.
Proven.
We're done.
Done.
So now we're solid, right? Well, that's going to help us out as we begin moving on. So keep those concepts in mind and how we can apply those. Write these down if you haven't already and refer back to them and understand how they relate to each other. It is very, very important. Finally, so let's see, yes, we have that. I want to make sure we have everything, and we have this. Okay, now we've got to do one more. We have the Pythagorean identities. Okay, so we will write these down, and these are listed just before your exercises begin. This whole table, this, and then what we're about to go over as well. So sine squared theta plus cosine squared of theta equals 1. One plus cotangent squared of theta will equal cosecant of squared of theta. And then finally, tangent squared theta plus 1 equals secant squared of theta. So, have those written down as well. All right, they will be very, very, very useful. Y'all have any questions? Okay, so take your problem solving concepts that we've learned so far and apply these. Now again, we actually have 7 sections in here. On 11.5, strategies for proving identities, I'm only having y'all do just a couple in that section. These 4, yes. These are, it will be useful to help you get into reasoning through this. So I'm not wanting to overwhelm you with the number of problems. I gave you these 4 to try to walk through and be able to prove them. This will be very, very helpful, very useful. So take your time and walk through. I'm not necessarily looking for which identity. I don't want you to necessarily have to determine the identity. I would just want to see your work of how you're proving it. Okay, so on that one especially, do step by step. Number 11.6. I believe I had, how many questions? 3 questions? Yeah, 1 through 3. This is, you're given a piece of information. Now what can you do with it? All right, so try to work through that the best you can. All right. And then finally, 11.7, there are only a few on there, but it's now going to use your radians okay, not degrees. And so remember the difference between where we have, where was I? Whenever we have degrees, we have our angle measure. Radians, we're dealing in terms of pi. Okay, radians is pi times whatever, depending on how we're moving around the graph or rotating. Or if we were to stretch the graph out into basically a timeline or a series of wavelengths, then you have your bands going from 1 to -1, going to half pi, pi, all the way up to 2 pi. Okay, so consider that when in dealing with those problems. Okay, reminding everybody visually, if you need to go back to chapter 10 to assist you with some of that if necessary, but it shouldn't be too difficult. I'm not, again, on 11.7, I'm not so worried about how in-depth we get with this. I'm really not. It's more just for exposure. So you can kind of see, and in the back of your mind, oh yes, I remember discussing that, but I don't want to put a lot of emphasis on it. I wanted to focus more on these first few sections because these are going to be more impactful as we go on throughout this chapter. And the typical class to take from here going into college is going to be college algebra or a trigonometry class. And this is going to be more beneficial going into that. All right? Any questions? Good job. Thank you for the participation. Y'all did really good. All right, good deal. We'll see you later on.